Let's make a start. So we have two talks today, which are going to cover connected papers. Our first talk is by August Geelmuyden, who's currently a PhD student at the University of Nottingham, and is going to tell us about sound rings in vortex clusters. So please, August, when you're ready, take it away.
You can all hear me?
Yeah, perfect.
Thank you very much for giving me the opportunity for this short introduction or explanation of our paper. So this is based on recent work that is during hopefully this week will be on physical review research called the sound ring radiation of expanding vortex clusters. So I figured I would structure the talk around the title and split it into three parts. And I will start by discussing or introducing Bose-Einstein condensates in general very quickly. So you know you have the interaction Hamiltonian in general. If you impose Bose commutation relations and a point-like interaction, then the mean field evolution of the wave function is given by the famous Gross-Pitaevskii equation. Notice here that I have taken out the chemical potential as a matter of convenience. So, by the way, everything I will talk about assumes two-dimensional condensates, so they will be vertically trapped by a strong confinement potential. There are three natural units or scales in the Gross-Pitaevskii equation. The first is if you consider a stationary case with negligible kinetic energy, then you get the Thomas Fermi approximation for a uniform condensate. The next is the phase cycle, that I like to call it. It's the time it takes the wave function to do a full 2π rotation. And the most famous one is perhaps the healing length, which is the length scale on which the kinetic energy and the self-interaction is balanced. Notice here that I don't have a 2 in the square root, so I like to keep the numerical factors outside. In these units, the Gross-Pitaevskii takes a purely mathematical form, and in the uniform condensate, the norm is an average equal to 1 of the wave function. And it's in these units that I will be presenting everything. So next thing that should be noted or known is this correspondence or hydrodynamic interpretation of the Gross-Pitaevskii equation. So if you introduce this new set of variables called the modelung transform, then the imaginary part takes the form of a continuity equation, and the real part takes the form of a Bernoulli equation, where this Laplacian term of the root rho is often called the quantum pressure term. So this means that we can identify the gradient of the phase with the velocity field and this modulus squared with the density of a irrotational Eulerian fluid. So one of the most surprising or strange things with this interpretation is that the velocity field being a gradient of a scalar potential means that there's seemingly no vorticity. So that might make you or lead you to conclude that there's no circulation around any loop of flow. But this is only true if the contained area is topologically simple. So in reality, you can make holes in the condensate called, and these are vortices, and they will be topologically protected and discretized by this phase winding ambiguity in the phase. So one of the most surprising or famous consequences of this is that if you rotate the condensate, then vortices come in and form this vortex array. This is the damped Gross-Pitaevskii simulation in the rotating frame. So that was a very brief intro to the basics of Bose-Einstein condensates. Now I'll take the next part of expanding vortex clusters. So the most naive guess you can make for the phase in such a wave function is just a plain theta single binding, or multiplied by LK here, and positioned around every set of positions where you would like your vortex to be. Then the gradient of this phase can be written as a complex function in 2 dimensions. And tricking a bit around, you end up with this classical point vortex model where the vortices move with a flow field constituted by all the other vortices. Notice here that in the velocity field, the vortices enter as poles. So for an example, for 2 vortices, you get the dynamics looking like this. So for counter-rotating vortices, they will move in a linear trajectory, and the boundary feels like a ghost vortex on the other side. And if you have some slight damping in a situation like this, they will annihilate and create a solitonic solution. Likewise, if you have counter-rotating vortices, they will rotate or orbit around each other at a fixed frequency that is inversely proportional to the squared distance. And again, if you have damping, the distance between the vortices will spiral out. So to add damping and noise, we are using the stochastic Gross-Pitaevskii equation, which effectively goes to multiply 1 minus I gamma in front of the Hamiltonian and add some stochastic white noise term. These are the damping and the noise is formally related to a fluctuation dissipation relation, where the variance of the noise is proportional to the damping and the temperature. So the simulations I will be discussing today are like this: a damped evolution of a 21 winding or charge vortex in the center. And you see in the beginning, it looks like a perfectly rotational symmetric situation. Now you will see that suddenly when the central vortex breaks into individual vortices, it creates a lot of waves. And notice in particular these counter-rotating waves. This is the signal that we will be discussing. And once it's expanded a bit more around here, now it's all understood through this classical point vortex dynamics. Waves are damped out and it's easy again. So it starts easy and it becomes easy. Well, not easy, it's a nonlinear thing. But the interaction between waves and vortices when they're close is especially tricky part. So we can split this movie up in 3 stages. In the first stage, we have a rotational symmetric vortex that acts as a single multiply winded vortex. In stage 2, there's this early decay of the multiply winded vortex, where vortices are very close together. They're intimately connected or coupled to the density waves in the condensate, and there's a lot of waves present. In the end, it's quiet again, and the dynamics is given by the point vortex, or a classical point vortex model. So for the remainder of this talk, we'll talk about this intermediate stage, which is the tricky one, where vortices are coupled to waves, and it's a highly non-equilibrium situation. And the way we will go about to model this is to use very crude and rough approximations. But then in the end, we will see that it fits nicely with numerical results. So even though we know it's not valid there, we will start with a classical point vortex model and do an azimuthal average and a temporal average of this model for a uniform distribution of vortices inside. The result is this Rankine velocity profile. Here, the red line is from numerical data from 50 simulations in the initial or the early part of that middle stage, and the blue is in the late part of that middle stage. And the change in those vertical lines is the expansion of the cluster in the meantime. A velocity profile like this can be thought of as the linear part inside is a solid body rotation of the cluster itself. and the outside is a rotational static velocity field. Likewise, we can do the same trick of averaging out all the rich azimuthal information in the background density. And this compares with the numerical results like this figure. So it does not fit that well inside the core because there's a lot of vortices inside. But outside the Rankine radius or the core, it fits very well. Here, by the way, this orange dotted line is the Thomas Fermi uniform condensate density that we would have had if there were no vortices there. So now we can talk about the sounding and radiation from it. So let's first mention sound waves. You have we have now talked about this density and phase and how we can make this rough azimuthally averaged and temporally averaged estimates for. And now we are going to consider small perturbations on top of this, and damping and noise is going to be small. And we assume that the background is moving slowly compared to the time scale at which waves propagate. Then you're left with a couple set of equations that are convective on the flow like this. And then we put in for the velocity field the background we just estimated, and the same for the density. These are the two curves we just saw. And in a situation of waves like this, we can first treat it as plane waves. So plug in a plane wave ansatz, and we write the phase in terms of polar variables. Now, the frequency will be conserved along the trajectories of these waves, provided that it's a time-independent situation, which it is approximately, given that the cluster expands slowly. And likewise, rotational symmetry conserves this azimuthal number m. Now, just a note on what this m means. So an m15, for example, plus 15 means that it's rotating with the flow, and it's a wave that has 15 peaks on the circle around the vortex. Last assumption will be a WKB expansion. So we assume that the wave phase changes much quicker than the amplitude of the wave. Then we are left with a dispersion relation like the one shown under here. Now, we can think of this dispersion relation as a phase space in radial phase space. So here on the x-axis, there's the radius, and on the y-axis is the radial wave number for a given azimuthal mode, for a given, in this case, it's m-15, so it's counter-rotating. And the arrows then show how the wave front moves. So first, we can notice this blue area. These are waves that never manage to get into the vortex, to the cluster. So these are waves that bounce off the potential boundary and bounce off the dispersion relation or the effective potential before next is this red region where waves are trapped. So they live and are trapped geometrically around the edge of the vortex cluster, which is this somewhat surprising artifact of the Rankine vortex profile. And the last region are waves that can communicate between the outer boundary and the vortex cluster. So crucially, there's a fixed point in this counter-rotating phase space. And this is exactly what the sound ring is, because the fixed point in radial phase space means that even though it's an unstable fixed point, if you trigger or tickle the condensate a bit there at the black diamond, then it will linger around radially while it's rotating, counter-rotating to the flow. So the wavefront will travel in the ring. Just to show how this fits into the simulations, this is what you should have in mind, where this is the scale. So that vertical dashed line is the size of the cluster, and the end is the boundary. And somewhere in between, outside the cluster, you have the sounding radius. So to build some intuition behind this, consider now you have an undamped system with infinite open boundaries, infinite system. Then you can put a lot of points in phase space and see how the system evolves. And all the waves will then be shot off. And importantly, you will see that they slowly bleed off at frequencies close to the sounding frequency. So these waves linger around and remember more what happened inside the core. Now in our system, we have reflective boundary conditions, so it's more like this. And the special part of the sounding is not really that obvious, but with damping and then decreasing amount of activity in the core, it's the sounding frequencies that will remember the previous higher wave activity in the core. So this is sort of the intuition behind why it's special. Another way of seeing this phase space is just plotting the dispersion relation. Oh, my internet is unstable. Can you hear me?
Yeah, we can hear you. It has been a little bit choppy, but it's
okay.
it's fine.
Okay. So one way of seeing this is through this volumetric surface plot, where this phase space is seeing this from above, and slices of constant frequency gives you the iconal trajectories of these waves. Now the bottom here is the co-rotating waves, by the way, which do not have a sounding or a fixed point. Another way of seeing this is from the side, where we get a plot like the one to the left here, which can be seen as an effective potential. So the existence of a maximum in the upper branch of the dispersion relation, labeled omega plus R of SR, is exactly sounding frequency. So just a note here that the negative frequencies, there's a symmetry in the system. So if you change the sign of the frequency, it's the same as changing the sign in the azimuthal number. So these correspond to co-rotating waves. The last way of seeing the predictions of this is by considering a radial average or a projection of the radius, in which these plots here would become just two lines, one for m plus 15 and m for m minus 15. And then you can do this for all azimuthal numbers to get a spectrum like this, where azimuthal number versus frequency. Here, all these dots are WKB estimates for the eigenmodes of the system, formed by the effective potential. And the regions are the same, and this black line here is the sounding that you can think of as sort of a fold in the spectrum. Now, the important thing is that this fold does not depend on time. These dashed lines are directly dependent on the size of the vortex cluster. So when the vortex cluster expands, these lines change, but the sounding does not. So now we run a lot of stochastic simulations of the decay, like the animations you just saw. Just to give you an idea of how much data this is about 15 terabytes of data. And then we consider ensemble averages. So first, for the effective potential plots, you get something like this. So the first obvious mismatch between the prediction and the theory is this highly excited region there in the forbidden region, where modes should be evanescent. But these corresponds to holes in the condensate. So just the actual single vortices moving around that messes with the analysis. So to study the spectrum emitted from the cluster, we take the largest cluster size in the window across all the ensembles, and we average radially from there out. And notice that from there and any other radius, it doesn't matter. The spectrum remains the same. There's also two striking features here with these lines, and they should be understood as the wave bouncing off the boundary and interfering with itself, creating this pattern, and the same with the potential boundary on the left side. And when both are present, you get discretization into eigenmodes of the system. So notice that you don't have both of them present in the bottom part of this plot and the top part of this plot. So if we now go to the spectrum, the data ensemble average for this kind of spectrum is very much like what we expect. There's a clear, for each azimuthal mode, M, in the counter-rotating part, the clear maximum is along this sound ring. And these feathers coming out here, these are the outer bound states predicted from WKB theory. But in the top part here, it's smooth. There's no bound states excited. So this is showing that the cluster moves too quickly, or the waves are feeling the dynamics of the individual vortices. And yet, the sound ring is strongly populated, exactly because it's outside the cluster. Notice also that the axes are logarithmic, so it's they are really highly populated, the sound ring. And as a concluding remark here, you can see this tail on the core-rotating part. This is closely related to, we think, to halfway this annoying thing with the holes moving around. And there is a small signal in there which is connected to what Sam will talk about. So to conclude, the important thing with the sound ring is that it's outside the cluster in the static part, and it depends only on the circulation density inside. So it means that you can have very violent situations inside the cluster with a whole range of complicated wave physics, and still these simple methods will inform you of where the bulk of the amplitudes will be, or the energy will be in the counter-rotating spectrum. It's also nice to notice that, or sort of the same thing, that the sound ring spectrum is present even when the whole wave assumption breaks down in the core. So when azimuthal modes are scattered to different azimuthal modes, when frequencies change and couple directly to individual vortex movement, the sound ring will still be, again, located outside and protected. And in the end, and this is sort of a bit more delicate of a conclusion or remark, is that this sound ring is it scales linearly with the charge of the cluster. So you have something like this where the sound ring scales with L, net binding, and compare this with the Rankine radius, or the core size, which for a fixed circulation density scales with the root of the binding. So it means that the larger the binding, the better the separation of the sound ring and the chaotic core. So you would expect this phenomenon to be more and more relevant for the more vortices you have. And eventually then the waves will also form bound states in the other regions. But this is very hard to simulate. So that was my talk. Should we take questions now, or?
Yeah, we can take questions now. Thanks very much for a very interesting talk, August. So time for questions before the next talk. So please, if you want to either pop something in the chat I can ask, or just raise your hand and ask directly.
I realized it was pretty quick. It's a bit of a time.
So I wanted I may have missed it. My son came and interrupted me at one point with a bleeding thumb. Did you also gain an understanding of how the radius of the Rankine, the sort of effective Rankine radius, increased in time? Did you have some sort of?
Yes, we matched it in the new the updated peer-reviewed physical review or PRR publication. We actually have a comparison in there. It goes as expected, as the root of something plus gamma time.
Okay, thanks very much.
Yeah. But we are the reason these data sets gets very big is that we need to have the separation of scales. So the window that's actually studied for the wave dynamics is so short that the Rankine radius almost does not change. That's the delicate. We do that to make sure that it's not the movement of the Rankine radius that affects the population of bound states.
Anyone else? Davide.
Yeah, thank you. Can you hear me?
Yeah.
Yeah, thank you very much. I just wonder if you have in mind any particular experiments that you would like to match your theoretical prediction to.
We have been talking to some people, but it's not settled yet. It should certainly be experimentally observable.
So do you reckon it's gonna be more like a helium experiment or more like a proper dilute Bose-Einstein condensate experiment? I'm just wondering.
Well, I think we can see it in both, and also in these exciton polyton systems potentially. This is as you see, it's a very rough setup. So, but we haven't, not to my knowledge.
Okay, thank you.
But we're aiming at doing with superfluids. That's something that will anyways happen.
Thanks.
I'm muted. Anyone else before we move on to the next speaker?